Hello, and welcome to the Star Party. I'm the real Mr. Science, your guide in all the adventures and explorations we will have here at the party. We are going to take a whirlwind journey from our Earth to the farthest reaches of our universe, with many stops along the way to observe interesting and exciting things. But with a little bit of help from computers, we will do all of that from right here. So get comfortable, settle back in your chairs, and hold on to your hats, because here we go. In the first part of our Star Party adventure, we will explore the solar system, the objects that orbit, that means revolve around, our sun. Astronomers call our sun Sol, which is Latin for sun, and we will follow that convention here at the party. This is a diagram of the solar system showing Sol, all the planets and other major objects that are part of the solar system. We will visit each one of them separately. Our first stop in our journey is Sol itself. Sol is many, many times larger than the rest of the bodies in the solar system combined. It not only dominates the solar system size-wise, but its existence is the reason we are here. The nuclear reaction going on in its core supplies all the energy the Earth has ever had or will ever have. All our oil, gas, and coal were formed from plants that grew from Sol's light and decomposed into those fuels when buried in the earth for millions of years. Wind energy comes from air movement caused by solar heating. Hydroelectric power comes from the flow of river water through turbine generators, but the water got into the rivers because Sol evaporated ocean water. Winds drove the evaporated water over land, where it rained down on the river's watersheds and flowed downhill to the generators. Of course, photovoltaic solar energy comes straight from Sol itself. Even the energy from radioactive decay that powers nuclear power plants comes from uranium left over from the formation of Sol. Sol is a huge ball of gas composed of about 94% hydrogen, about 5% helium, and 1% of everything else. At Sol's center is an essentially solid core, comprised of about 10% of Sol's total mass. The core is also a gaseous mix, but with a higher proportion of metallic elements, due to the compression of Sol's immense gravity. The core is 20 times as dense as iron. It is in Sol's core that heat and compression result in nuclear fusion, with atoms of lighter elements, mostly hydrogen, being forced together to form heavier elements, like helium, and in the process giving off immense nuclear energy, just like a hydrogen bomb. Sol is, in effect, a gigantic hydrogen bomb, which has been continuously exploding for billions of years and will do so for billions more. Before we travel away from Sol to the rest of the solar system, let's talk about the relative size of the objects that we are going to visit and the distances we are going to have to travel to see them. We can easily put numbers on them, of course. For example, Venus is about 8,000 miles in diameter. The Earth orbits the Sun at an average distance of 83 million miles. Jupiter is about 89,000 miles in diameter, and so on. But those numbers are kind of meaningless to human beings. We don't regularly travel 83 million miles, or most of us even 8,000. Instead, we all live at a human scale, where an average person is between 5 and 6 or 6.5 feet tall, The supermarket is a couple of miles down the road, and the jet plane flying overhead is 20,000 feet up. With the human scale as our daily experience, it is very difficult to comprehend the mind-boggling hugeness of the universe, or even the vastly smaller, but still immensely large solar system. Some comparisons, however, might help. This chart shows the size of objects in the solar system measured by something on the human scale. Let's assume that the sun is really a kid's soccer ball, just 8 inches in diameter. On the same scale, the Earth would be the size of a peppercorn, the biggest planet, Jupiter, the size of a chestnut, and the small dwarf planet Ceres merely a pinhead. The objects we are going to visit may be relative. Our first stop, the first planet out from Sol, is Mercury. It is a small rocky world, but with an iron core. Mercury is only about 1.5 times the size of Earth's moon. It is, in essence, a somewhat oversized and much hotter version of Earth's moon. Mercury, like the Earth's moon, has no atmosphere and virtually no water. Its closeness to the sun means that on the sun-facing side of Mercury, temperatures soar to 800 degrees Fahrenheit, while on the side in darkness, they fall to minus 300 degrees. NASA's MESSENGER spacecraft did detect what appears to be water ice, hidden in the deep shadows cast by craters near Mercury's north and south poles. Mercury, the planet, was named in antiquity for the swift messenger of the Roman gods, probably because Mercury, the planet, moves around Sol so rapidly. NASA's spacecraft was named Messenger because it is exploring Mercury. In the youthful solar system, Mercury was blasted by meteorites and other debris left over following the consolidation of the primordial solar nebula into the planets, and so has numerous craters, some newer ones overlying older ones. In places, lava flows have covered older craters. These pictures of Mercury's crater surface from the Messenger spacecraft mission to Mercury look like they could be images of Earth's moon taken by an Apollo mission. Next we come to Venus. Still something of a mystery, as befits the planet named for the Roman goddess of love. Venus is only a little bit smaller than the Earth. It has a dense, opaque atmosphere, however, which makes optical observation of its surface almost impossible. Several Russian Venera spacecraft have landed on Venus, or at least entered its atmosphere, without landing. But Venus' extremely hostile environment limited the data that was returned. These probes showed Venus was neither the idyllic garden of love of classic mythology, nor the humid, hot world with tropical plants and strange, swamp-dwelling creatures of early science fiction novels, but instead was a forbidding place with a harsh, acid chemical atmosphere many times denser than Earth's, oven-like surface temperatures, and active volcanoes in large numbers. Magellan's radar built profiles of the Venusian landscape, including mountain ranges like these. And it even identified a huge volcano called Mat Mons, showing its recent lava flows. But despite Venera's and Magellan's explorations, as befits the goddess of love, Venus still has many secrets awaiting discovery. Of course, the next planet out from Sol is our home, Mother Earth. This is the Earth seen from one of the Apollo spacecraft on the way to the Moon. The Earth is a rocky planet with extensive oceans and an extremely hot liquid iron core. Take a good look. It's our home, mankind's only home, and we are going on a long, long journey away from it. Let's tarry a moment, though, to look carefully at the Earth's constant companion, the Moon. This image is of the near side of the Moon, the one we always see from Earth. It's a composite of multiple images to enhance the lighting of its surface features. Gravity has locked the Moon into a rotation that exactly coincides with its orbit around the Earth, so we only see one face of the Moon from Earth. Most of the planets in the solar system have moons, but Earth's moon is unusual. It is very large in comparison to the size of the planet it orbits. All the other moons in the solar system are much smaller compared to the planets they orbit than the Moon is compared to Earth. That's because the Moon was probably formed when a huge asteroid collided with the primordial Earth. The resulting debris reformed into two bodies, the Earth and the Moon. The other moons in the solar system are probably gravitationally captured asteroids instead of having formed at the same time as the mother planet. Even from your backyard, you can see that the Moon has many craters. Here is a picture taken from orbit around the Moon by one of the Apollo missions. This crater is named Copernicus, in honor of Nicholas Copernicus, the Polish scientist who first postulated that the Earth and the other planets revolved around the Sun, rather than the Sun and the other planets revolving around the Earth. It is huge, 60 miles across and 11,000 feet deep. Most of the Moon's craters formed millions and millions of years ago, when the bits and pieces of rock that had not consolidated into one of the planets continued to orbit around the solar system and frequently collided with the larger bodies. Likely, billions of meteorites hit the Moon, and the larger ones formed craters like Copernicus. Even more probably hit the Earth, but 2/3 of the Earth's surface is covered by oceans, and the land masses of the Earth are subject to erosion, volcanoes, mountain building due to continental drift, and similar kinds of action that erodes away evidence of a collision. Any scars left by meteorites that did not hit in the oceans have largely disappeared over the millions of years. The Moon, on the other hand, has little geologic activity and no natural erosion, because it has no atmosphere and no water, except for perhaps some ice perpetually frozen in the shadows of craters near its poles. So most craters formed even millions and millions of years ago still survive. Some of the early scars and craters left on the Moon have been covered up by later but still ancient volcanic activity. The molten rock formed large, smooth basins. Lava covered existing craters, creating a surface like a lake or a small ocean. Early observers of the Moon, through telescopes, thought that these basins were in fact water lakes or oceans and called them mare, Latin for sea. This is Mare Crisium. We now know that they are large, smooth, volcanic plains. Early telescope observers apparently failed to appreciate that some mare have permanent craters on them, just like the ones found elsewhere on the Moon, something not possible in a real ocean or lake. These later asteroid impacts scarred the mare, and the lack of weather on the Moon means the craters have persisted until the present. So now we say goodbye to our home world and its satellite, and move outward into the solar system. As we leave Earth's orbit, we can see the far side of the Moon. The intense meteorite bombardment endured by the Moon and the early solar system is evidenced by the huge number of craters on the Moon's far side, many overlapping each other. This is also a composite image made to enhance the view. No planet besides the Earth has been so carefully and extensively studied as Mars, the fourth planet out from Sol. Part of the modern fascination with Mars grows out of the belief that in the far distant past, Mars did have water, and perhaps even life, although we now know that life most likely would have been bacteria and similar animals, not creatures like you and me. A modern image of the Martian surface shows Mars has no significant surface water today. The idea that Mars had water on its surface originated with the first telescopic observers of the planet. This drawing is by Italian astronomer Giovanni Schiaparelli, who, in observing Mars in 1877, believed he had detected water canals, along with large areas of growing crops using the water. Of course, it was all a mistake. Modern telescope photographs, and then the many interplanetary probes that have traveled to Mars, show that Schiaparelli's canals and huge farms were optical illusions, and probably not a small amount of observer wishful thinking. Mars has a rich and varied but dry topography, which in the early astronomers' eyes became the physical manifestation of a Martian civilization. That myth persisted due to science fiction novels such as H.G. Wells' War of the Worlds and Edgar Rice Burroughs' stories about a mythic chivalric kingdom on Mars. In fact, present-day Mars is dry, as it has been for millions and millions of years, although there is substantial evidence that in the distant past Mars did have a significant amount of water. Some indications are that even today there is some water left on Mars, probably in the form of ice, under thick layers of rock and soil. This image shows what looks like a sedimentary rock formation, which likely formed in a sea or lake just as such formations do on Earth, but when Mars still had surface water. The best evidence that Mars once had water are the numerous meteorites knocked off Mars by volcanic eruptions or asteroid collisions billions of years ago, which wandered around the solar system until they, by chance, were captured by Earth's gravity and landed here. From information provided by NASA's Mars rovers, we know the unique isotopic composition of the Martian surface, and so know these particular meteorites came from there. While tiny amounts of water have been discovered in these meteorites, a recently found meteor from Mars, measured to be about 2 billion years old, has 10 times the amount of water previously discovered. 2 billion years ago, evidently, Mars was a wet place. Mars has 2 tiny moons, Deimos and Phobos, most likely asteroids that wandered too close to Mars and were captured by its gravity. Jupiter's huge gravity creates strange groupings of asteroids outside the asteroid belt itself, much closer to Jupiter's orbit around Sol. The combined effect of Jupiter's gravity and that of Sol caused 2 large groups of asteroids to orbit Sol in the same orbital path as Jupiter, but at 60 degrees ahead and 60 degrees behind, respectively, of Jupiter in its orbit around Sol. These locations are called the Lagrangian points, after the astronomer who discovered the effect. Whimsically, the two groups of asteroids are called the Trojans and the Greeks, after the two warring sides in Homer's Iliad. The larger objects in each group are named after characters in the saga. The process of asteroid formation by collision resulted in many asteroids with non-spherical shapes. Here is a collage of images of Vesta, Eros, Ida with its moonlit dactyl, Gaspara, and Itokawa, all of which are in the asteroid belt between Mars and Jupiter, but which do not orbit anywhere near one another. The biggest object in the asteroid belt, Ceres, is large enough to have sufficient gravity to make it more or less spherical. It looks like a small planet. In 2006, astronomers decided to restructure the classification of the objects in orbit around Sol. The 8 largest bodies that are spherical, by collision or gravitational influence, have cleared out any other bodies that may have been in their orbital area, and are not themselves satellites of another body, are called planets. We have visited Mercury, Venus, Earth, and Mars so far, and will visit 4 more shortly. These 8 bodies are the big guys, the planets in the solar system. The other classification of larger bodies in orbit around Sol is dwarf planet. Dwarf planets are those bodies that are large enough in mass to be spherical in shape and are not satellites of another planet. But dwarf planets have not cleared their orbits of other bodies. Ceres is a perfect example of a dwarf planet. It's large enough to be spherical and is not a satellite, but it sure has not cleaned out its orbit through the asteroid belt of other objects. NASA's Dawn spacecraft is on its way to Ceres, and in a couple of years we should have a lot more information about it. There are 4 other officially recognized dwarf planets, and we will visit them later on in the star party. Jupiter's gravity creates strange groupings of asteroids outside the asteroid belt itself, much closer to its orbit around Sol. The combined effect of Jupiter's gravity and that of Sol caused 2 large groups of asteroids to orbit Sol in the same orbital path as orbital. Beyond the asteroid belt, we enter the realm of the gas giants. We are 135 paces from our soccer ball-sized Sol, about 5 times as far from Sol as is the Earth. And we've arrived at the kingdom of massive Jupiter. Named for the principal god of the Romans, its size and brightness as seen from Earth make it the undisputed dominant planet in the solar system. Its physical characteristics match its mythological reputation. It is about 87,000 miles in diameter, about 11 times that of the Earth. Its mass is 318 times that of the Earth. Its orbit around the Sun is about 480 million miles in radius, and it takes 12 years for it to fully circle Sol. Jupiter has a metallic core and a huge envelope of gas, mostly hydrogen and helium, which circulates around the planet at speeds faster than the speed of sound. The atmosphere divides into 9 major belts with somewhat different compositions and velocities of motion. For centuries, a gigantic cyclonic storm, a sort of hurricane, except that it's on Jupiter, has raged in Jupiter's southern hemisphere. Called the Great Red Spot, it is large enough to swallow 3 Earths. Observations over a couple of centuries show it is gradually growing smaller, but a separate, similar cyclonic storm has begun to develop in a different location. Not only is Jupiter the biggest planet, It also wins the Solar System Moon Sweepstakes. Jupiter has 50 confirmed moons, plus 16 more that have been identified but not confirmed. 4 of the Jovian moons are large enough to have been discovered by Galileo in 1610, when he was one of the first astronomers to make use of a telescope. These moons are champions in their own right. Ganymede, the largest moon in the solar system, is larger than Mercury and 3/4 the size of Mars. Io is the size of Earth's moon, but unlike the geologically dead moon of Earth, Io is violently volcanic, spewing mostly sulfur and frequent eruptions. Callisto is a rocky world the size of Mercury. Europa is an ice world the size of Earth's moon. In addition to its moons, Jupiter boasts of a small ring of dust and fine rock particles, perhaps from small moon collisions in Jupiter's crowded neighborhood. Jupiter does have some competition for the title King of the Planets, because, even though it is somewhat smaller than Jupiter, assuredly, Saturn is the most distinctive planet in the solar system. Like Jupiter, it is a gas giant with an iron and rock core and a deep atmosphere mostly of hydrogen and helium. It too has bands of gas rapidly circulating around the planet. But its appearance is less distinctive than Jupiter because the bands are not as brightly colored. It's about 72,000 miles in diameter, about 9 times that of the Earth. But in addition, and distinctive among all the planets, Saturn has a crown, its giant disk of so-called rings. Jupiter has but one small one, unremarkable. Saturn's rings dominate its appearance. They're composed mostly of ice crystals, rock dust, pebbles, and a few larger rocks that agglomerate into bundles, an inch or two across at most in most instances, but with few as large as a mountain, all orbiting around the planet. Of course, they run into each other and break up, reforming in new agglomerations. The gaps between the rings are caused by the gravity of Saturn itself interacting with its many moons. 2 small moons actually orbit in more or less permanent gaps, visible in the ring system. Saturn rings are never fully face-on as seen from Earth, but during parts of Saturn's orbit around Sol, they are tilted enough to give us an incredible show of the crown of Saturn. Like Jupiter, Saturn also has many moons, 62 to be exact, mostly small ones associated with its rings. But Saturn does have one of the most interesting large moons in the solar system, Titan. It is the second largest moon of any planet. It's larger than Mercury, and is the only moon of any planet to have a dense atmosphere. It is a fascinating cognate of Earth, but with hydrocarbon seas and rivers, a dense nitrogen and methane atmosphere, weather patterns, and rocky surface features. These images were taken by the Cassini spacecraft and the Huygens lander, which touched down on Titan. Even deeper into the void lie 2 smaller gas giants. The first is Uranus. Uranus is much smaller than Saturn. It's only about 4 times the diameter of Earth. Uranus' atmosphere is mostly hydrogen and helium, like the other gas giants, with a small amount of methane and traces of water and ammonia. Uranus gets its blue-green color from the methane gas in its atmosphere. Its core is thought to be liquid ammonia and other gases. Uranus's orbit is way out there. It takes 84 Earth years to complete one orbit around Sol. Unique among the planets, Uranus' axis of rotation is almost perfectly parallel with the plane of its orbit around Sol. All the other planets in the solar system have axes that are nearly perpendicular to the planes of their orbits around Sol. Astronomers are still working out why Uranus is that way. Uranus does have a lot of moons, 27 of them, all named for characters in Shakespeare's play A Midsummer Night's Dream, or in works by Alexander Pope. Most are very small, but Titania and Oberon are about the size of Earth's moon and resemble it. The moons shepherd Uranus' small rings in much the same way as Saturn's moons shepherd its rings. The last planet outward from Sol is Neptune. It is dark and cold, and its hydrogen, helium, and methane atmosphere is whipped by supersonic winds. Neptune is just about the same size as Uranus. It orbits Sol at a distance more than 30 times further out than the Earth, so it takes almost 165 Earth years to complete its orbit. In 2011, Neptune completed its first orbit since its initial discovery in 1846. Like Jupiter, it has gigantic cyclonic storms. By good fortune, a very large one developed just as NASA's Voyager 2 spacecraft was flying by Neptune, enabling Voyager 2 to capture this picture of Neptune with its transient Great Dark Spot Storm. Like Uranus, Neptune has numerous moons, 13 to be exact. It also has several small rings. One moon, Triton, orbits Neptune in the opposite direction from that followed by its other moons, suggesting it was an asteroid-like body that was gravitationally captured by Neptune as it sailed by. Triton has ice volcanoes, but it is not yet known the source of the energy that causes them. The 2006 reclassification of solar system bodies created the new description dwarf planet. Ceres in the asteroid belt is one, and the outer solar system has 4 more official dwarf planets. In addition, several recently discovered objects may be dwarf planets as well. The dwarf planets orbiting Sol, essentially outside the orbit of Neptune, are called Plutoids. Plutoids are named after Pluto, which, until the reclassification, a planet in its own right. Pluto was discovered in 1930 and was regarded as a planet until the 2006 changes. Pluto is now a dwarf planet and is joined by 3 other newly recognized dwarf planet, Plutoids, that also orbit outside Neptune in the cold, dark reaches of the solar system. They are Makemake, Haumea, and Eris. All are small rocky bodies, although all but Makemake are known to have tiny moons of their own. These bodies are so small and so far away that there are no images showing them in any detail. Makemake is named for the creator of mankind and the god of fertility in the culture of the native people of Easter Island, the Rapa Nui. Haumea is named for the earth goddess in the Hawaiian pantheon. She is the mother of Pele and 2 daughters, Hi'iaka and Namaka, whose names grace Haumea's 2 known moons. Eris is the largest of the known dwarf planets and is about 25% bigger than Pluto. It is named for the Greek god of strife and discord. When Eris' moon was discovered, it was named for Eris' mythical daughter, Dysnomia, the goddess of lawlessness. This is all very appropriate since Eris has a very unusual orbit, highly inclined to the general plane of the orbits of the other planets and dwarf planets, and very elliptical. Several other distant objects orbiting beyond Neptune are being investigated as serious candidates for classification as dwarf planets. They are Sedna, Orcus, Koa-Or, and one yet to be even provisionally named, so designated as 2001 OR-10. Some of them even have moons. The Plutoids inhabit one of the two most distant realms of the solar system. The closer of the two is called the Kuiper Belt, named after astronomer Gerhard Kuiper. The Plutoids are in the Kuiper Belt, along with what are probably millions of other small bodies, all circling Sol in their own distinctive individual orbits. Even further out from the Kuiper Belt is the Oort cloud. The Oort cloud was named after astronomer Jan Oort, who postulated it. The cloud is a vast spherical cloud of comets, perhaps as many as 2 trillion of them, orbiting the Sun at almost unbelievable distances far, far away, but still just within the influence of Sol's gravity. Occasionally, a chance encounter between 2 Oort cloud objects or a passing cloud of interstellar gas and dust will cause a comet from the Oort cloud to fall into the inner solar system. There it may take a highly elliptical orbit around Sol, often glowing and trailing a huge luminous tail. If the orbit is just right, it may be captured into a long-term orbit around Sol and periodically reappear, like Halley's Comet, until its ice and gases have been evaporated entirely. Occasionally, a comet will come too close to Sol and will either collide with it or simply burn up from Sol's heat. At least one comet came so close to Jupiter that it broke up and eventually collided with that planet. The outer edge of the Oort cloud is the edge of the solar system in many senses. Beyond the Oort cloud, no object is under the influence of Sol's gravity. But in another sense, the edge of the solar system lies far beyond the edge of the Oort cloud. Sol exercises its influence over its brood of planets, dwarf planets, asteroids, and comets in an important way other than just its immense gravity. The outflow of energetic particles from Sol's nuclear furnace is called plasma, or sometimes the solar wind. The Earth feels directly the effects of the solar wind. In its orbit around Sol, the Earth sweeps up a small part of the solar wind, which is pulled down to the Earth near the Earth's north and south poles by Earth's magnetic field. The solar wind collides with the Earth's atmosphere and shows up as the northern and southern lights. The plasma that flies off Sol into the emptiness beyond the planets at a speed of about 1,000,000 kilometers per hour forms a huge ovoid around Sol and the solar system. It is ovoid because as Sol follows its orbit around the center of the Milky Way galaxy, it plows through plasma and dust emitted by the galaxy's billions of other stars, millions or even billions of years ago. Sol's solar wind collides with the galactic interstellar plasma, and its outward motion is brought to a halt by that interstellar plasma and pressed back along the leading edge of Sol's orbit around the galaxy center, while trailing out behind the solar system like a comet's tail. Astronomers call the ovoid zone protected by Sol's solar wind the heliosphere. Helio for the Greek sun god Helios, and sphere for its general shape. In any event, helio-ovoid would be a mouthful, so we use heliosphere instead. The leading edge of the heliosphere lies about 12 billion miles from Sol. The surface of the heliosphere, where Sol's influence completely ends, is called the heliopause. Just inside the heliopause is the heliosheath, where Sol's influence and that of the interstellar medium contest one another as their plasmas collide. The heliopause is thought of as the boundary of the solar system, but Voyager 1, which is near the heliopause, has shown that the boundary is not a fine line. Instead, Voyager discovered a chaotic mass of interacting particles, gas, dust, and plasma from both Sol and the interstellar medium. Voyager's making good progress through the heliosheath toward the heliopause and the complete edge of Sol's influence. When Voyager crosses that border in the next few years, it will become mankind's first interstellar spacecraft. And luckily, it may tell us a lot more about what interstellar space is truly like. This image is NASA's artist's conception of the Voyager's long journey to the heliopause and beyond. So that is the solar system, home to Mother Earth and a lot of other interesting things. In episode 2 of the Star Party, we will leave the heliopause far behind and explore the part of the Milky Way galaxy that Sol was now passing through. Astronomers call this galactic neighborhood the Orion Spur of the Sagittarius arm of the Milky Way. We will call it Sol's galactic neighborhood for simplicity's sake. It's a nice neighborhood and full of interesting things to look at. Thanks for dropping by. Come back soon to the Adventures of the Real Mr. Science website and check for Star Party Part 2, Sol's Galactic Neighborhood, coming soon to a computer near you.